Hello everyone, my name is Jacob Hill. I'm a doctoral student in information science at the University of North Carolina in Chapel Hill. In this video, we're going to examine a few of the overarching structures, or meta-models as I will refer to them, that are commonly found in different organizing systems. So meta-models are patterns that appear repeatedly across different domains. Different people working in different fields come up with similar solutions independent of each other. A meta-model then can be defined as the convergence of these solutions. So for example, biologists attempting to organize and describe the various species of life on this planet, and computer scientists designing file structures for an operating system have both adopted a hierarchical tree structure. This structure can be found in many unrelated systems and thus can be viewed as a meta-model. Information system designers, when creating models of their domain, rarely create entirely new models. They usually choose between existing meta-models. These choices have important implications for how we interact with our data, what our systems are capable of doing, and even the type of questions we ask about our data. So modeling the various species of life as a tree, for example, encourages students who are learning about the different species to think of them in the context of this hierarchical structure. In reality, however, there is nothing inherent in nature that suggests that it should be described as a tree. Many people have proposed other models. A common model is the web of life, in which the species are depicted as a web that lacks the same hierarchical structure. Finally, when thinking about designing an information system, it's important to consider the goals of the project as well as the strengths and weaknesses of different meta-models. Some approaches, some meta-models will be more appropriate for different problems. So adopting an iterative approach that shifts between these two perspectives, the needs of the project and the strengths and weaknesses of the meta-model, could be very effective in developing a system most appropriate for our problem set. So now we'll take a look at some of the types of structures or meta-models. So a very common and simple structure is a blob. A blob is a paragraph of text, an image, a video. Blobs lack any formal structure beyond grammar. Another is a set, which is a group of unique words with no discernible order. A list is the same thing as a set with one additional constraint, that the items are now an ordered collection of terms. Dictionaries are lists or sets of key value pairs. A tree can be viewed as a collection of nodes and edges with a single root node, or perhaps as a nested dictionaries with the constraint that the top dictionary has only one entry. More precisely, a tree is a graph of nodes and edges where each node has only one parent but may have multiple children. And finally, a graph is a set of nodes connected by edges that may or may not have a direction. The parent-child relationship is not inherently imposed in graph models. So a tree is a type of graph that's constrained by the fact that it has to have a single node, single parent, and that each parent may have multiple children. So other types of structures that we could look at, which could be considered hybrid structures. Though this is not a hard and fast definition. In reality, many of the structures could be considered hybrid in some respects. Are a table, which could be viewed as a list of dictionaries or a list of lists, and a relational database, which is in a sense a graph of a list of dictionaries. It's really a graph in which each table is a node. So now we'll take a look at each of these structures in more detail. So a blob is just a paragraph of text, a sentence of text. It could be a video, it could be an image. It's commonly used if we want to convey information for humans because it most closely relates to how humans express themselves. So it's great if your audience is a human. It's not such a good approach if you are going to rely on machines to process the information. Because it lacks formal structure, machines will have difficulty processing it. So a set is just a group of terms without order. It could be useful if you just want to create a group of keywords or tags, for example, in which order is irrelevant. A list is the same thing as a set with an additional constraint that order is important. This could be useful in programming, if you want to manipulate the list by the index of each term. This is a common data structure used in computer science and programming languages. A dictionary is similar to lists and sets. In lists and sets, there is no way to distinguish the items, however, except by comparing their values. Or in a list, you can use the index or the position of each term or item in the list. In dictionaries, however, you can look up each value by its key. So we can find that Leo Tolstoy is the author by searching for the key author and getting the value Leo Tolstoy. So JSON is a common example of a dictionary type structure that's used frequently. Dictionaries are also used a lot in a programming language. And they could be useful if you need a simple model, but one with more structure than a set or a list provides. So a tree is a graph of nodes and edges in which each node has only one parent, and all of those are traced back to a single node. But each of these nodes could also have multiple children. So trees are great if you have a simple organizational problem in which all of the items you wish to organize can be divided into clear groups. So the resources in a library, for example, can often easily be divided into types of book or video or article, for example. Moreover, each of these types, each member in the category or class of books, for example, shares common traits with the other members. So they inherit certain qualities from the class that they're in. So every book has a title, every book has an author, for example. Graphs can be useful in problems where you can't necessarily discern a clear order or grouping. So in dealing with the species of life on this planet, um, they don't. Every member, every instance doesn't always fit nice and neatly into a hierarchical structure. Yet we may wish to express that. So graphs could be useful in dealing with situations where uh, we can't gain a bird's eye view and divide everything into nice, neat groups. They can also be useful for combining knowledge. So if you have two different groups of people working on a similar problem or an overlapping problem, and they find that it's useful to share data later on down the road, um, if they've modeled their data in a graph, it will be much easier to do that because their graphs are schema neutral. So combining the graphs will be much easier. So graphs can be very useful in situations that can't be broken down into nice, neat groups in which you desire flexibility, and there's a good chance you might want to combine your data with other groups down the road. Uh, Graphs could be a good approach. Um, Earlier in the video, I mentioned that designers of information systems rarely adopt entirely new models. Most are either identical with existing models or they are some type of hybrid structure. Tables are a good example of this. They share some features of dictionaries and some of lists. They can be viewed as a list of dictionaries in which each cell in each row combined with the corresponding cell in the header row forms a key value pair. Or if the header row were to be removed, the meaning or context associated with the contents of each cell would be lost, in which case we would be left with a list of lists. The advantages of tables are that they're very intuitive, they're portable, and they're technology agnostic. People can, training is very simple. Most people know how to understand how to use a table. And it doesn't really matter which operating system you're working on or what type of device even. We can use tables on our cell phones or tablets or computers, on Macs, Windows, Linux, in the cloud. It really doesn't matter. We can exchange data across all of these systems. And finally, relational databases, which can be viewed as a graph of tables in which each node is a table. Relational databases are great at handling complex data, optimized queries, and another advantage is that the software market is very mature. We've been working with relational databases for a long time, and we've developed a lot of software around them. In reality, it's probably the most, aside from a table, it's probably the most common, robust, it's definitely the most common robust organizing system or structure. So disadvantages, one of the main limitations of relational databases is that they're heavily schema dependent. So if you want to change something, if you've developed a system of tables and the relationships between those tables, and you decide that you want to add a new data set to that, a new table to that, you have to change the whole schema. You can't just easily adapt it. And another limitation of that, which is another facet of the same problem really, is that if you want to combine two different relational databases, say, two teams of biologists working on the same problem, the tree of life, they decide they want to team up and join their data, chances are they didn't just intuitively design the same exact schema. So you have to write special software to translate between the two databases. And you can't always do that exactly term for term. It will, at the very least, usually take a lot of work and a lot of money to combine data. So relational databases are great if you need a robust system, and it's very stable. You're not going to need to change it, and you're not going to need to combine your data set with others. You're certain of those things. Relational databases could be a very good solution for you. So thank you all for watching. I hope this video was a useful introduction to data modeling. Those interested in exploring the subject in more detail may wish to consult the discipline of organizing, specifically Chapter 8, which I used as a guide in creating the slides for this video.